Okay, so there we go. Okay, so sorry everyone for the Google Meet issues, but we are collected on Zoom. Um, so today, for the colloquium today, we have lucky to have Nancy Rodriguez. She's a professor at the University of Colorado Boulder. Some of you may remember her from a 2020 MCRN summer school on COVID. Certainly was great to interact with her there. She got her PhD from UCLA, and then she had an NSF postdoctoral fellowship at Stanford. Her research concentrates on nonlinear partial differential equations, specifically those pertinent to urban crime, segregation, biological aggregation, chemotoxis, and ecology. And today she'll be talking to us about collective behavior in online to offline systems. And so with that, very much looking forward to the talk.
Thank you. Thank you, Christian, for the invitation. Thanks everybody for joining. And I apologize for the technical issues, but I'm glad we have figured it out. Today, what I want to talk about, of course, this meeting is being recorded. Hopefully that will, just when I think it's working. Oh, there we go. Okay. So the work that I'm going to discuss today, it's really falls under the umbrella of learning dynamics and detecting causal pathways in coupled offline, online to offline systems. For me, what kind of interested me in this was basically that social instability is increasingly connected to a dynamic interplay between online and offline systems. So I'm just giving you like 3 examples of what I mean by an online to offline spillover, right? So these are 3 examples of things that have happened, right? So there could be a Facebook taunt between gang members that leads to offline retaliatory gang shooting, right? That's online activity that's leading to an offline activity. Or you could have a preprint posted on medRxiv claiming a high risk of vaccination for adolescent males, which is picked up by the media, somehow, ends up on social media, spread there, and so reinforces vaccine hesitancy, which again is an offline consequence. Or closer to what I'm interested in, you may have a video of a security force beating a street vendor, which again is viewed and shared online, and that brings thousands of people to the streets, right? This is exactly what happened in the Arab Springs. So really the picture that I want you to have in mind is what I have down here. Is just you have this online world, people interacting on some social network. There's some maybe call to action in some form or another that leads to an offline activity. I personally am interested in protests, but there could be other activities such as boycotts, right? Domestic violence is a big one actually in the UK right now. There's a huge increase in domestic violence, and it's due to social media. But the increase is believed to be due to social media. Hate crimes, vaccine hesitancy, right? That in turn, of course, it's either picked up by the media or people tweet or go on X, and that returns back to online. So here's sort of an outline of the talk. I will, these are all projects that fall within this umbrella. And so I want to focus on 2 modeling frameworks. One, kind of inspired by the summer school that we worked on together with a lot of you. So that's an epidemiological approach, but also because I work on PDEs, we will also discuss a reaction-diffusion approach on networks. And then time permitting, I will focus on sort of what happens on just the online network and talk about some experiments that look at trying to understand the effect of networks on consensus. Okay, so again, for the first part of the talk, the motivating question is how do protests spread in the age of social media, right? How do social networks influence protest dynamics, right? So 2/3 of the population use social media. And so it has really fundamentally changed when, where, and how conflict occurs. There are many benefits, of course, right? This can lead to increased mobilization, organization, increased awareness, right? You don't need leadership. It could lead to international support, as we have seen in many movements. And it can lead to a sustained online support. But of course, there are drawbacks, right? There could be government surveillance. Most important to us, I think it's sort of this spread of misinformation and disinformation, and also like superficial clicktivism or like movement fatigue. So from the modeling perspective, right, again, we want to provide frameworks to try to understand these spillovers. So we're going to look at an epidemiological approach where, again, especially after the COVID-19 pandemic, a lot of us understand these, right? These are just compartmental models whose theory has been generalized to include network dynamics. We'll really start with the work of Burbick, who from what from what we can tell, is the first work that really used this approach to understand riots in 1979. We took that approach to introduce spatial spread to understand the 2005 French riots a few years back. And then since then, actually, people have generalized that approach to look at things like to study the spread of Chilean riots that happened in 2019. So I'm going to first focus on that, but then I will then talk about sort of reaction diffusion models. That's a different framework, right? Reaction diffusion equations are used to model general phenomena, and there's a huge theory developed for these models. The benefit of this framework, right, is that if we want to understand spread, one way that we do it in reaction diffusion models is to study traveling wave solutions and look at the spread, right? Just the spread and basically the qualitative behavior, stability of these waves. And we already have a model developed to understand, to model protesting dynamics in this framework. And there are actually other people who have introduced similar models as well. But then we can just move that to a network and try to understand the spread of activity on the network. So let's start off with the first approach, the epidemiological approach, right? We can use a multi-layer network to incorporate this coupled online-offline effect. So in online, we have a network and we call this the information layer, and we divide people into people who are either uninterested in a topic, they become engaged by interacting with someone who's engaged, right? So it's someone in their social network. And the parameter here, the transmission rate is tau, and this is per individual interaction. Eventually, people become disengaged, right? We have this kind of movement fatigue. And a fraction of the people engaged, so we are making this assumption that only a fraction of the people engage protest. So we are assuming that everybody who's protesting is engaged online with a rate of transmission to protesting being eta. In the physical layer, right? Again, either people the default state is not protesting, but it's really not part of the dynamics. So what a fraction of the people who are engaged online protest and then eventually recover, right? So this is one model, right? Eventually, to try to introduce a framework and understand how we can introduce the network structure. But of course, then given data, you'd want to, do model selection, right? But these are the assumptions that we're working under. So we can think of this as a stochastic Markov process, right? In this case, we only have 5 states, and each state actually has an online and offline component, right? So these are the 5 states that are, so people start from uninterested, not protesting, they become engaged, right? A fraction of them, a fraction protest, they become disengaged, again, another assumption, become disengaged online, and then they recover at some rate online and offline. So again, as usual, we want to keep track of the expected number of individuals in each of these states, in particular engaged and protesting. And so for these expected values, we have, again, for the stochastic process, the exact differential equation, and it's a matter of like closing these equations, right? So here are just sort of the dynamics, just to illustrate what's happening. We have an online social network. In this case, imagine that people are just offline boycotting, so physical space doesn't really matter. And there are a few people that are engaged online. They start other people begin to engage, and then a fraction of those start disengaging. So you see that not everybody who engages online, so these 3 people engaged online, they did not protest, right? So not everybody necessarily protest. So that's just an illustration of what the stochastic process is doing. So, again, what we want to do is be able to approximate the number of edges, right, connecting uninterested individuals with engaged individuals, ensuring that we have a good approximation without an excessive cost, right? So of course, the first thing that you start with is assuming that everybody is interacting with everybody else, and we have the typical closure here. And let me just sort of show you the dynamics for this case before we try to introduce network topology, right? So here, looking at the fraction of people in each one of these compartments, these are the types of dynamics that you see. First and foremost, you should focus on the red and purple, because that's the engaged online, and then the people protesting. You can see that there's a shift, right? Basically, the engaged is the reservoir, right? The pool of people who will be protesting. So it's always going to be a delay, but sometimes it's a more sustained delay offline, depending on the parameters, right? On the recovery rates. Okay, so the benefit of doing this, of course, is that you could, we all know this, look at the reproductive number, right? And there are 2 questions of interest, right? When do we expect online outbursts of activity? And when does this online outburst actually turn into an offline outburst? And if you think about it, right, just the stochastic reproductive number, it's just going to be, assuming initial online activity, it's going to be beta, which remember is tau, I didn't mention it, but it's tau times the number of people in your network, divided by eta plus gamma I. So you can see that essentially your pool for people protesting is C, and if you're draining too quickly, then you don't expect an outburst of activity. But even if you have an online outburst, if eta then is too small, you won't have people protesting. So then you don't have an outburst offline. So eta, there's a sweet spot for eta. It can't be too large or too small for there to be an offline outburst of activity. This can be seen more clearly when you actually approximate, use the next generation method to find the reproductive number. You can see that eta has both an enhancing but also an inhibiting effect on this reproductive number. And so you see this sweet spot that eta, has to kind of live in. But so this is kind of the reproductive number that we can see. What I'm showing you here in this figures is just the maximum activity online, depending on varying this R naught. And you can see that again, for the online engagement and the offline engagement, you begin to see an increase in the max number of activity as you cross this threshold 1. Okay, all right. So that's if everybody's interacting with everybody else, but what if we start introducing network topology, right? So if we have, just starting off with a k-regular graph, so everybody has an average degree of k, or everybody has exactly k, not an average degree, but exactly k neighbors, then you could do multiple approximations that we want to compare, right? So there's a single level approximation that's very similar to the fully mixed model, except now you have k over n here. And it's a very cheap model. It's 5 equations. Well, in reality, it's 3, because we can get rid of the equation for D online and R offline. Or you can do basically look at the evolution of the edges, and then you have to do a closure with respect to the triplets. And there are various ways that you can do it. But in the end, for us, we end up with just 2 additional equations here in this case. But again, we have sort of the closures, which I'm not going to go into the details on those closures, right? But you're making approximations based on the fact that this is a homogeneous network. And so I just want to show you, mostly I want to show you, I'm going to, skip all the mathematical details and just show you some of the results. So if you look at the online engaged here, this is a network of 1,000 individuals with a degree of 5. The stochastic model, basically we use Gillespie, and the envelope is in blue, and the average is in this dark blue. You can see that the single level approximation here in red, it's not as good of an approximation as a pairwise approximation, right? The pairwise is spot on because you're keeping track of the evolution of the edges. As n increases, the single level approximation doesn't seem to do any better. What's happening is just that our pairwise approximation, our envelope is getting smaller, right? As we assume, because it's a larger network, and we did a mean field approximation. Same thing for the offline activity. The pairwise approximation does a much better job approximating the system, because it turns out because it's a low density network. So then it makes sense to try to study for what networks, right? Because the pairwise is a more expensive model than the single level. When should you use it? And if you look at the average or the degree in fixed and large, right? The pairwise always does pretty well. And the single level begins to improve maybe after K is 25, especially for the offline. You can see that they're basically the same. If K is slow, so for the bottom graphs, K is 5, the single level approximation, even if n increases, will never improve, right? The pairwise will improve, although it's always a pretty good approximation, right? So essentially, the pairwise approximation, again, it's superior for low dense networks, right? So, but if your network is very dense, then, single level approximation is good enough. If you have a heterogeneous network, right, then we really want to keep track of not only the number of individuals who are uninterested or engaged, the total number, but we want to break it up into their degrees, right? So we now want to keep track of the number of individuals who are engaged, who have only one neighbor or 2 or 3 or 4, up to some K maximum degree, right? So we have a lot of like synthetic heterogeneous network, right? And Erdos-Régnier power law networks, bimodal networks, and real life networks are actually heterogeneous, right? So the price, of course, that we have to pay is that we go from 5 or 7 differential equations to that number times K potentially, right? So you have a lot more of these. But you can play the same game and do either a single level approximation where you're not keeping track of the edges. And I'm not going to go into the approximations, but essentially, again, these are the online networks. And again, now you have to multiply this times the max number of degree. Or you could do a pairwise approximation where you are keeping track of the networks. There are a lot of different approximations that you can do. We chose a compact approximation because that for us worked well enough for the networks. So let me just show you, I mean, the benefits of this, of course, is that now you can break the dynamics of what's happening online and offline by the degree, right? So here you can see that the dynamics is really driven by engaged individuals who have an average degree of 5, right? Or have a degree of 5, not average, but have a degree of 5. And then next is the individuals, right? The population with degree 3 and degree 7, because in this network, there are more of those, okay? But you can then break the dynamics of the engaged by degree. Well, how do the approximations do? Again, you can see that, here we have an average degree of K. You can see that the compact pairwise approximation is pretty much spot on, right, on the Gillespie. So it's a pretty good approximation, whereas a single level approximation that doesn't keep track of the topology of the network um, doesn't do as well. I mean, it's not terrible, right? At least it's predicting that you will have an outburst. It just tends to overestimate the activity. And in general, it tends to overestimate the activity, and also like the peak comes too early. This is an example of a bimodal network. So just to illustrate that if you have a network that is very dense, so here my two modes are average degree of 30 and 70, so it's a pretty dense network. Basically, the compact pairwise and the single level approximations are right on top of each other. So for dense network, and the compact pairwise in this case is way more expensive than the single level. So you wouldn't want to use that. But if your density is low, so here we have one mode of, average degree 2 and degree 8, you can see that the single level approximation is way off, right? So again, the pairwise in this situation makes sense. Okay, so we tested it in all sorts of synthetic networks. The pairwise does very well. And then when you test it on real life networks, the pairwise and the single level don't seem to be that different. Okay, so what our approximations can do is they're very good at approximating, like determining whether we're going to have an outburst versus not. And in the case where there's no outburst, both approximations do very well approximating the dynamics. But for some parameter regimes where you have an outburst, our approximations are not as good as on the synthetic networks, right? And the pairwise is always better, but it's not as good as it was for the synthetic networks. So so there's work to be done here, and I'll tell you about it in what we're doing to figure out the closures in a minute. But for now, we have these approximations, right? And so you want to be able to explore what the effect of, let's say, maybe the average degree is on the activity. And one thing that you learn is that as the network becomes more dense, the max proportion of people engaged online increases, right? As you would expect. But offline, it basically plateaus very quickly. So that online activity is not, even if when the network becomes more dense, is not translating to offline activity. Okay, so of course, having these mean field models can help us find, I'm just showing this for the homogeneous approximation. This is the single level approximation. This can help me find the reproductive number. The line is equal to 1 is this line here. And of course, then we can help classify, right, when we expect to have an outburst of activity versus no outburst of activity. And of course, further away from your line, you see a clear activity. Closer to the line, you just sort of see a small engagement, which eventually decays as we expect as you get closer to that border. And the same thing for the offline. But let me just, the question then becomes, which of these approximation can help you classify a protest, right? Whether you're going to have a protest or not. And well, the question is, what do you classify a protest, right? How big does it have to be? And according to NPR, the magic number is 3.5%. So 3.5% of your population has to be eventually protesting for change to potentially, for this to actually lead to change. And in that case, actually, both of our models are very conservative, and they overestimate the regions of protest, right? Really, the pink line is the reproductive number that comes from the pairwise approximation. So it is a better approximation for the R naught as well. The orange versus blue comes from the stochastic simulation, right? So it's stochastic simulations, running a lot of them, and then thresholding, right? So if you threshold at 3.5%, you can see that both of our lines are really overestimating, what would be a protest. But certainly the pairwise approximation is a better approximation than the single level approximation. Okay, so ultimately, so we have this framework, right? We know for what networks you should use a single versus a pairwise. We want to connect this to data, right? And in terms of offline protests, there's data. There's this organization called ACLED that keeps track of all sorts of conflicts throughout the world, but it's based on newspapers. So there's not sort of complete information, and you're not tying back to an online component. So the first thing that we're doing in our moving towards that direction is to first understand sort of like the social component. Currently, we know that there are bots online that are, large language models, and we want to understand how those different large language models lead to potentially different reproductive numbers, right? And so what we have here is, this is current work where we're basically have networks of large language models that are tweeting, we're fitting in real life data from ACLED, and based on the severity on these issues, they're either tweeting, and then their neighbors are reading and retweeting, and then we can look at the reproductive numbers. And for now, what we can see is that different large language models have different reproductive numbers, right? And so we're using like Wendy to try to find these reproductive numbers. And I'm not going to talk about this slide. Let me move on. But in terms of like for this project, what we're currently doing is, okay, we're trying to use weak Cindy to try to find better closures for the real life networks, right? Because there's something about the network structure that our approximations are not taking into account. They're reasonable, but they could be improved. And then ultimately we aim to connect actually the online data to the offline data, but that's been more challenging than we expected. So that's where sort of things stand for this framework. And so now let me switch to the reaction diffusion approach, where now we're taking a model that was developed for sort of physical space, where you're looking at the level of activity. Think of this as like if you have a Poisson process, it's like the number of protests is a Poisson process with conditional expectation U. This is how U evolves, right? The conditional expectation evolves. And it is coupled to a social tension, right? So we know from the sociological literature that in order for protests to occur, you need, well, usually a triggering event, but coupled with a high social tension, okay? And so we've developed this model with a while back based on, social theory, but also interviews from people who participated in the 2005 French riots. And basically, these functions here model things like relaxation, right? Tension. There needed to be a sufficiently high tension for activity to occur. Self-reinforcement, right? So this self-excitement, and then diffusion of these activities. So this function R models the switch mechanism so that if V is too low, the self-excitement is not going to turn on. This is a self-excitement. And then H is the coupling between the two unknowns, which turns out to be a really interesting parameter, because if K naught is positive, this is basically an enhancing system, right? A cooperative system. But if K naught is 0, it's an inhibitive system. So U inhibits the social tension, and both actually seem to be to appear in data. So the natural thing to do, of course, is we know that these reaction-advection diffusion or reaction-diffusion models exhibit traveling wave solutions, monotone and non-monotone. So what happens now in reality of this tension now is diffusing online, right? We have this information diffusing online. What happens can we understand that spread just like we did in physical space, but now in a network? And so the natural thing to do is, of course, for spread to just spread through this graph Laplacian. And the figures that I'm showing you here, right? So these two on the left are the traveling wave profiles for the reaction diffusion. What happens on a network? So if you have, this is an Erdos-Régnier network, and you just happen to pick a parent node, and then, anything that's within distance 1, let's call it like shell 1, and then anything within distance 2 is shell 2. And so what you could do is kind of average along those shells what your value U and value V are. And then you can visualize these traveling wave solutions and how this activity is spreading. And so in this situation, I'm illustrating, there are two different types of waves. I can either, was there a question? I heard, okay. Feel free to interrupt me. So so you have your parent node and say everybody within a certain distance of the parent node has U high. Eventually, right, like you could invade the entire system. In this case, time, I'm illustrating 3 different time snapshots. So red is the initial condition, and then the next time is green, and then purple and blue. If you see 4 different colors, there you can see the evolution. If you don't, it's because the wave has been pinned. So eventually there are situations where there is no transmission and these traveling waves are just pinned. There's also the situation where the periphery of the network can be engaged. And in this case, what we see here is you do have some pinned waves, but also you can sort of see an invasion, right? And so the idea is, can we try to understand what the spreading speeds are depending on the network, right? And the parameters, right? So that's sort of what we wanted to understand. We wanted to explore these push, pull, and pin wave regimes depending on our parameters. And let me just say that, for those of you who have worked in ecology, these are the different reaction terms that appear. Now, it's a system, so they're not really what I'm illustrating here. But if you assume that V equilibrates very quickly, essentially you end up with a situation where in some parameter regimes you have a strong Ali effect, you have a weak Ali effect, or you have a Fisher KPP. And so depending on what regime you're in, the situation and the spreading is going to be different. So those are the things that we want to explore. So let me just show you what I mean by these 3 regimes. So this is the equilibrium solution for U that I'm illustrating only, right? Then there's one for V, but I just want to illustrate U. You can see that here I'm fixing all parameters, but let's look at the one on the right. If I increase gamma, you go from 1 equilibrium solution to 3, and then back down to 2. Right? So the 3 would be the weak Ali effect, and then the 2, it's either Fisher KPP or weak Ali. So let's understand what happens in the Fisher KPP regime. So, okay, so for simplicity, we're going to work on an R-ary tree, okay, which is locally a reasonable approximation for an Erdos-Régnier network, at least locally. So in this regime, we can use asymptotic analysis to find the spreading speed. So first of all, you need gamma is a parameter for the self-excitement, and this is for the decay. You need this to be positive, right? So there has to be enough self-excitement for there to increase activity. So these are the spreading speeds for D1, very large, right? So the diffusion of U very large or very small. The difference between what happens here and what happens in physical space is that in physical space, the larger the diffusion, the faster the spread. In this situation, there's some maximum diffusion depending on how many branches every node has. And the more branches you have, the smaller the maximum diffusion, right? So essentially, if your diffusion is too large, the reaction can't keep up with the growth. And so there's no spread of activity, which is very different from what happens in physical space. And as R increases, you can see that that maximum diffusion gets smaller and smaller and smaller. Okay. In this case, because the Fisher KPP is a situation where your waves are actually pulled by the edge of the front, essentially the speed is going to be the linearized speed. And so you can compute that. And so we have here this black line is our linearized speed. And you can see we run simulations in both black, blue, and red, depending on different diffusion rates. And the approximations and the speed is spot on until K crosses some threshold, this K naught. And that's we're moving away from the Fisher KPP regime, right? So we're moving away to sort of a push regime where the entire wave is pushing the front. So I'll briefly talk about this case in a second. But within the Fisher KPP regime, what you see here is sort of depending on the diffusion, our approximation, that's in black, and then our simulations are in red. And you can see that, in fact, our spreading speed approximation is spot on in that regime. So what happens when I cross over here? Well, I'm crossing into this pooled regime. And so really in this case, we were only able to understand the binary network so that, everybody only has two neighbors. And even then, the asymptotics are not as good as in the Fisher KPP regime, but as the diffusion gets smaller, basically the simulations here is in blue. This is the linearized speed, and our asymptotics is giving us this red or this orange line. And as the decreases, then this blue line does get closer to the orange, right? But we more or less know, have an approximation of as you cross into the weak Ali effect, how the speed is going to change, okay? And the last regime is kind of an interesting regime because this is a situation where you can have pinned waves, okay? Of course, this does happen in physical space if you happen to have like heterogeneous medium. But if you don't have heterogeneous medium, you don't see this, right? So in this case, you can try to understand when you're going to have invasion of activity or when your activity will retreat, because that's possible if the initial activity is not enough nodes are sort of infected, or when it's going to be pinned, right? So again, waves of the first kind are waves that again start in the periphery, right, with your parent node, and then either spread or don't, or maybe they stay pinned. This is again a simulation for the Erdos-Régnier network. So this is a situation where you have a pin wave. This is a retreating wave. This is a situation where your activity is actually, right, your nodes are actually becoming disengaged, if I were to use the terminology from the first part of the talk. Anyway, you can basically separate space to try to understand when you expect to have retreating waves, invading waves, or pin waves. Without showing you the math, let me just tell you, right? So I chose two parameters. DU should be D1, but it's the diffusion of U. And K is related to R. It's just R minus 1. So that's how many, right? How many branches a certain node has. And for waves of the first kind, right? So if only nodes in the periphery are engaged, actually, so for regions 1, 2, and 3, you actually have pin waves. So this activity will just remain there. It kind of equilibrates very quickly to something that's kind of smoother at least. But the wave never invades. And in the region 4, in fact, your wave retreats. No, so for waves of the first kind, you never have invasion. Waves of the second kind, when the periphery of your network is engaged, what we can see is that there are pin waves only in region 1. It's a very, very small region. And then in the remainder of the regions, you do have invasion of activity. Okay. So this is the only regime where you have actually pinned waves, right? And also retreating waves. In the other regimes, you always have invasion, and the question was, how fast was it going to invade? In this region, you may not have invasion at all. Okay, so Christian, I mean, I started a little late. I can talk about another project that, talks about consensus, but I could also stop there if we want to have more time for questions,
Oh,
since we started a
yeah,
little earlier.
yeah, we started a little late if you wanted
Late,
to.
sorry.
Yeah, I think if you, I'll leave it up to you if but we did start a little late, so I think, yeah, if you wanted to continue, that's okay.
Okay. Yeah, so this should only, it should only take less than 10 minutes, so we should be able to finish on time. But I did want to share sort of, so the other works were sort of looking at sort of the online to offline coupling and the spillover. Now I want to kind of focus on the online component, and really focus on like how the network actually affects consensus, right? And so this is interesting because we are working with experimentalists with a group of psychologists at UCLA, who basically ran the experiments, and then we just developed the mathematical models to try to understand sort of the dynamics. And this was work motivated by an experiment done by Santola and Boroncelli back in 2015, where they paired individuals came online and they were assigned to a network. I'll tell you what the network topologies are. And each round they were paired with an individual, and I'll show you the networks, and they're shown a face, like this face. And the goal for the two individuals who didn't know who the other person was to give a name to this person. And if they agreed, they would get a score, they would get a point, and if not, they wouldn't get a point, right? So they are incentivized to agree on the name. So let me tell you a little bit more about the experiment and then how our group generalized it. So this is basically one of the networks, right? So everybody's connected to everybody else. Each round, you can see everybody's paired with someone. They're shown the same face. Again, hopefully if I heard the name Emily the first time, maybe the second round, I'm going to say Emily. And so the number of names that you hear should be decreasing. And this actually from the experiment, right? So it does actually decrease. So so let me show you the two topologies. There is this homogeneous network. Everybody's connected to everybody else. And then there's a spatial network where you're only connected to your 4 nearest neighbors, right? So somehow this is spatially embedded. And you can see, right, the transmission of information it's only, again, everybody's connected to everybody else, but you're really interacting with the same people, the same 4 people, even though you don't know it, right? So what our team did was kind of generalize, right? So the phase task was a control task. So they developed a second experiment where individuals first read a narrative, specifically on the Fukushima narrative, and they were asked to create hashtags. Okay, so now instead of being shown a face, you have to agree on a hashtag. right? But it's the same setup. You either have a homogeneous mixing network, you have a spatially embedded network. There are 40 rounds that occur. Either you have the phase name task or you have the hashtag task. If you agree on the hashtag, you get a point, and if you don't, well, you don't get a point. There's also a post interaction that our group is interested in, but that's not really what we're interested in. So let me show you some of the results on the different networks. Now, it's very difficult for you to see names and hashtags, so we color-coded them. Each name is color-coded, and each hashtag is color-coded. On the x-axis, you see the trial number. On the y-axis, you see participants. Of course, you know, they kind of wrap around for the spatial, but just for illustration purposes. And then the first column is homogeneous network. The second column is spatial network. The first row is phase experiment and then hashtag. So there, something that emerges from the homogeneous network is a fanning, right? Eventually, right, you see a lot of colors in the beginning, and eventually red begins to fan out, right? Red dominates. So there seems to be a convergence to consensus, more or less, not everybody. But on the spatial network, this is also true for the hashtag, okay? For the spatial network, what you see are stripes. So you can see local consensus emerging, but not global consensus, right? And somehow you see kind of these boundaries forming, even though everybody's communicating across boundaries, eventually you kind of align to one group or the other group. This is true again in the hashtag. So in order to develop models, right? Well, you know, you may think of using like game theory, but here are the strategies that people are using, and this is how we divided the strategies, the potential strategies of either people are choosing to repeat themselves, that's RS, repeat their partners, they're bringing in new information, which sometimes they do, that's brand new. Or earlier context is maybe a name that they didn't hear the previous trial, but a name that they heard 3 or 4 or 5 trials ago. But it's part of like they've learned. It's part of something that they heard during the experiment. And an interesting difference between the phase and the hashtag is that in the beginning for the phase task, no matter what network, the use of brand new name drops significantly after the first trial, right? Very quickly. Now, for the hashtag, that's not the case, right? For the hashtag, people are still bringing in brand new information from, you know, a lot more than you would expect. This probably is related to the fact that the phase task is a simple task. The hashtag, basically, you may think, well, maybe I said hashtag nuclear and you say hashtag disaster. Maybe I think hashtag nuclear disaster is a better hashtag, right? So it's a more complex task versus a name. You know, it's like you just want to make the points in that case. So we develop a couple of models. One is, you know, we call it the context-aware agent models, where individuals are learning. And by learning is, you know, learning to not use brand new information, right? So I'm leaving all the mathematical details behind, but essentially it's sort of like an agent-based model. And the key thing is that basically you have a parameter alpha that measures how fast individuals are moving away from using background knowledge to using social context. And the two things that should not be surprising is that in the phase name task, individuals are learning very quickly, whereas in the hashtag task, individuals are not learning as quickly, right? The results that you see here at our top is basically the entropy decay, the Shannon entropy. So the faster it decays, the faster the convergence. From the experiment, we see that there is a faster, well, there is no convergence. There's no global convergence for the hashtag, for the spatial networks. And so our result here the simulations are in, so this is the model are the triangles, right? And so our model pretty spot on matches the entropy decay for the 4 different conditions. A model that Santola and Boricelli introduced is a very greedy model. They just assume that individuals are very, very rational, and so the entropy for them decays very quickly, but that's not what you see in the experiments. Because we've learned individuals are not making optimal decisions, right? If an optimal decision would be you repeat yourself or you repeat your partner. Okay, and so you could also fit the data to see how individuals learn, because it is clear that within a certain experiment, individuals are learning differently. And so now I'm introducing a parameter to either repeat yourself and repeat your partner. It seems like half of the time individuals repeat themselves and half repeat their partner. But again, in the phase name task, and I should have put this is the orange, you have lower individuals in generally, right, are learning faster than in the hashtag. But of course, you do have some distribution, some individuals who just never learn, actually, and just bring in brand new information. And I think they probably do it on purpose. But anyway, to try to understand, to gain insight, into sort of what's happening, right? You can look at simple models like, what if you are in a homogeneous network where everybody can interact with everybody else, and there's only 2 names, right? Just for simplicity. And you can look at sort of the fraction of individuals saying name A or hashtag the first, one hashtag versus the other. And you can look at the probability of switching to a neighbors, right? So if you're paired with someone who agrees with you, nothing happens. If you're paired with someone who does not agree with you, then you switch to your neighbor's name with, let's say, probability P. And so in the mean field limit, you can get your stochastic differential equation and a Fokker-Planck equation, and you can then look at the mean field passage time, and essentially P is equal to 0.5 optimizes, right? It minimizes time to consensus. So half the time you want to repeat yourself, half the time you want to repeat your partner. So what happens when you incorporate earlier context? Or when you incorporate, let's say, a matrix structure to introduce space? Those are the things that we're looking at. But it seems like adding a little bit of earlier context actually can decrease the time to consensus, because if you're stuck in a local min, it kind of pushes you out. So bringing in a little bit of like brand new information is not necessarily a bad thing. It could actually be helpful. Okay. I think I've spoken enough, and it's almost 2 o'clock. So let me just thank the NSF and the Army and my collaborators, the students who do all the work, of course. And thank you for your attention.
Great. Thank you, Nancy. That was a really interesting talk. It's cool to think about these things in reaction diffusion equations. It's interesting. I think Nancy, if you have time and people have questions, if anybody has one, is that okay with you, or do you need to run?
Yeah,
or-
I don't need to.
Okay.
I don't need to run. I have time.
Okay, yeah. Yeah, let's open the floor.
I have a question.
Yes.
Okay, so then if you go back to your net compartmental model,
Mm-hmm.
right? So when you have the online and offline ODEs,
Mhm.
so you have R0 that you're spitting out, right?
Mhm.
So in a typical like like SERR model, you have different different states that you are, or different R0. So there's, when you're less than 1, you could go to stable disease-free equilibrium, for example. There's unstable disease-free, then endemic, unstable endemic equilibrium. But so you're not looking at like what happens to R0. I mean, what happens to your states? I mean, as far as like how R0 is controlling that.
Yeah, so you can look at, yes, they're different states. And so you can look in Moy, they did do an analysis of like what happens, like what state you end up in. So you can certainly do that, and I didn't talk about that. My main interest here was how can this help us determine whether we should expect an outburst of activity versus not. But absolutely, you can try to understand based like what state you're going to end up in.
I mean, the reason why I asked this question is because when you have diseases, like there's this herd immunity thing, right? So basically, enough people get infected, then the disease go down. But do you have this thing in terms of opinion dynamics for you? Like as
Well, so we're assuming it depends on the time scale, right? So we are assuming that with, because certainly you know, you don't necessarily have herd immunity in opinion dynamics, right? But so we're just assuming that this is like one event, right? And so eventually people obviously can become re-engaged. But for this time scale, we're assuming that it's only a short enough time that they don't have time to be able to become engaged. And certainly that's something that, you can extend or look at a model that incorporates that.
so a follow-up question is about the networks. So how do you implement this Facebook networks, this real life? I mean, how does that work for like your network modeling? So you're not using Erdos, like for example, when you're using Erdos for any random networks. I mean, this is something specific.
Oh,
But
so
how,
these are specific. We happen to have access to just some specific friendship networks, right? There's no randomness to those networks. These are just a few networks that we have access to. Yeah, so
okay.
these are just, yeah, friendship networks from Facebook. And actually, we met someone from Reddit who is willing to share some of the data. So we're hoping to get more of these networks where you have like people following certain people, right? So in those cases, they're going to be directed networks, right? So then we have to kind of extend the model to looking at those directed networks. But the same idea, it's like you can generalize these models. It just for directed networks are going to get more complicated.
I think there's somebody that raised their hands there.
Oh, yep. Yeah, go ahead.
So I think Jan Sieber.
Can you hear me?
Yes.
Yeah, so I mean, it was maybe a follow-on question because I mean, you tried these different like generic networks like Erdős-Rényi and the other ones. Like, what would be a reasonably, say, realistic model for a social network where I expect you have strong preference for triangles and things like this, while Erdős-Rényi never has triangles?
Yeah.
Like,
Yeah.
what was the good like that creates the right amount of clustering, etc.
So first of all, power law networks are like it's like there's a lot of these networks, I don't know whether they truly are power law, but people say are really like reasonably approximated by power law networks. And actually these these approximations work really well for power law networks, but somehow there is something right there. I think it is like the clustering that our approximations are sort of not taking into account that even like the three real life networks that we have, like, like uh, there must be some sort of clustering that we need to take into account. So it's not just, like even if power laws, it's claimed that they do a reasonable job approximating, there's something missing there.
Thanks.
And Nancy, I'd ask a question. Thanks for the talk. A lot of really interesting problems. Can you show the last project you did, the stripes versus kind of consensus figure?
Yeah.
Yeah, so I found this one really fascinating. So I was wondering, I mean, it doesn't sound like you kind of repeat these experiments, but I wondered kind of if the size of these stripes had some sort of like, selection mechanism, or if you could determine kind of like as a maybe thinking of these as like pinned fronts or something, if the kind of people that were sitting right at the boundary of these interfaces, maybe had a certain personal characteristic or something, or if that's something you've thought about or investigated.
Yeah, so it's very difficult. Well, it's very expensive to run these experiments. And like they're, I think we're basically done running the experiments. And so we are trying to analyze the different characteristics of individuals like who are maybe like agreeable to try to understand, if there's certain characteristics, like you said, of like where, because these boundaries could be placed, could happen anywhere, right? And so I think there is some data analysis that can still be done to try to gain some insight into that.
Okay. Yeah, like where your mouse is right now, there seems to be two people that just never change their mind the whole, or three people maybe even that just are
Right. So
very
this
stuck in their
person just
ways.
kind of never always like, I guess maybe they didn't say anything the first trial, and after that, no matter what they heard, they stayed. And so there was sort of the talk of, trying to understand the effect of, like, what if you have one person who is very stubborn, right? Sort of like an influencer, right? So that's something that we can do with now that we have these models, even though we can't run the experiments, we can at least play around with all sorts of things to try to understand the effect of things like that, right? Like people who just always repeat themselves, right? And see how that affects. So that, that was sort of the goal, is like, let's find some models that do a reasonable job with the dynamics, so that then we can explore all of these things.
Yeah, no, it's really interesting. And if I could ask one more question, it would be on the transition to the push to pull fronts, right? So you have this kind of estimate, and can you kind of briefly say how you came up with the asymptotics here?
Yeah, so I think this is for yeah, so this is for the binary tree. So in the case you have the binary tree, you can then approximate this with a reaction diffusion equation. So instead of being in a discrete, you now have a PDE, which then you can analyze that. So this is the speed that this PDE approximation gives us.
So it's like okay, I see a lattice kind of approximation. Okay.
Yeah. Yeah.
Thank you.
Last question for me at least.
Go for it.
In your context-aware agents model, you're talking about fitting the data and fitting data. What does that mean? Are you estimating parameters? Is that what you're doing?
Yeah, so you can do we took a Bayesian perspective to basically we're fitting, and let me get back to every single individual given, so here, of course, we're kind of approximating what their decision is, right? Because we only have the name or the hashtag, but we're saying, okay, if you're repeating the same thing that you said before, that's repeating yourself, repeating partner, if it happens to match, then we're saying we're 50-50 assigning that. But you have sort of this data set, right? And you also know how many points everybody agreed. And so we use priors. So we use priors based on like all the data that we collected, but essentially like you're finding like the distribution for every single one of these individuals. And, so here's, for example, a distribution, well, an approximation, a smooth out approximation of these parameters. But yes, we're individually fitting each in every individual. So there's not a lot of data, of course, right? Because there's basically for each individual, there's like 40 decisions that they made.
Okay, well, I appreciate it. Thank you. That's what I got.
Okay, anything else? Any other questions? Okay, well, yeah, thank you again, Nancy. That was really
Yeah,
interesting.
my pleasure.